and we discussed that basically it is complementary because I have a PMOS block and I have an NMOS. This is a pull down block and this is a pull up block, and every input like A is connected to one transistor in the pull up and one transistor in the pull down. So when A is 0, the PMOS will be on, the NMOS will be off, or when A is 1, the PMOS will be off and the NMOS will be on. Yani the input turns one of the two transistors at a time, and because of this, what happens is that a given combination of inputs, a given combination of inputs is going to turn on a path either in the input block, pull down block or pull up block. يعني 0 0 will turn those two and will connect the output to VDD, or the 0 1 will turn off the pull up and will connect the pull down to ground, like in here or in this case. So you should be familiar with these concepts. If you have any issues, let me know as we speak. Then let us see now what is the generalization. So I have an NMOS pull up, pull down network and an PMOS pull up network, and what happens is that the inputs and the networks are arranged such that one is on when the other is off. Yani we do not operate or turn on both at the same time. Okay, let us look what happens if, so we operate either the pull up is, pull down is on and then the output will be 0, or the pull up is on and the pull down is off. Okay, and then the output will be pulled up to VDD. Okay, so we operate at only those 2 points. We do not operate in cases where both of them are off. If both of them are off, the output will be floating. I don't know what's going to happen to it. And if one of them, both of them are on, what will happen? If it happens that this is on and this is on, what will the output value be? Will it be 0 or 1? It will be somewhere in between, right?
The average?
It will be in the middle, right? Because I will have R up and R down, right? So we don't want this to happen. We want the output to be a clear 1 or a clear 0, so they cannot be on at the same time. One of them has to be on. Okay, so this is why we operate where one of the, either the pull down is on, pull up is off, or vice versa. Okay, so we operate at those 2 possibilities, and this is what complementary CMOS logic is. Later we will see other types of logic. Okay, طيب great. هلا, if we want now to generalize the types of gates that we have studied, we will see that we also have a 3-input NAND, and in this case y is equal to A and B and C bar. The way to draw the circuit is as we learned in 3.11. We will start with the function y bar. It is equal to A and B and C, so the pull down will be on if and only if y bar equal 1, if and only if y equal 0. يعني I have a path to ground. Okay, and this happens when y bar equal to 1, meaning when y equal A and B and C. Okay, and as we have seen in the behavior of the pure switches, if they are NMOSes, so the pull down, I always build it from NMOS, and they are active high, so I can have correlation. So the ANDs is really A series, B series, C. So I put A in series with B in series with C. Okay, the pull up is typically the complement of this. So for the pull up, I use PMOS devices, and the series becomes parallel, and the parallel becomes series. In this scenario, we will have A parallel to B parallel to C. Okay, I assume most of you are comfortable with this concept, and we will take more examples. Okay, anybody has a question? Okay, great. So now we have here, this gate is the 3 input NOR. So the function here is y equals to A or B or C bar, which means y bar equal A or B or C. The pull down is A parallel to B parallel to C, and the pull up is really A series with B series with C. So you can see here you have 3 transistors in series, and the input A is going into the different N and P devices. Okay, so this is very basic revision. Now, if I have a complex CMOS gate, for this CMOS gate, what we will have is, let us draw it on our own and then see how the slides work. Okay, so the gate that we have on the next slide is A and B or C and D bar. So given that we have here Y is equal to A and B or C and D bar. Even if it was not bracketed, I start bracketing the original expression. So this has precedence, this has precedence. So Y bar will be equal to A and B or C and D. And for this now, we can replace this by a series, this by a parallel, and this by a series. Okay, so if I want to draw it, I start with the innermost blocks within the brackets, which are the AND. So I will have A and B, or A in series with B, and all of this will be in parallel with another block, which is C in series with D. Okay, these are in parallel now. This is my pull down network. It is finished, so it should be between out and ground. Okay, then we will write the pull up network. So this is for the pull down. Now for the pull up, I keep the same bracketing, meaning A and B were together, then C and D together, then I acted on those two, and I flip the series to parallel and the parallel to series. So now if I want to draw the pull-up network, I have to start with A parallel to B. So I have two PMOSes, which are A parallel to B, and these are PMOSes. So this is A and B. And then the same block, I have another block C parallel to D, and the whole thing is in series. So I have another block where I have C, and this C is in parallel to transistor D, and those two blocks are in series. So let us make little way here for this. And those two blocks are in series. This comprises my pull-up network here. and the whole pull-up network should be between VDD and the output node. Okay, so it should be between VDD and the output node. Okay, I could have put C parallel to D up and A parallel to B down, but what matters is that this is the first block that I execute, second block that I execute, and then they are in series. So anybody has any question?
Yes, Professor, I have a question.
Sorry.
Just to be sure, the input.
Mm.
Where's the input here?
The inputs are A, B, C, and D, right? So practically
Oh, yeah, sorry,
speaking,
I thought there has to be a single point.
these are one input, right? But for simplicity of the drawing, we do not connect the wires. This is the same node, so it's the same signal, right?
Yeah, sorry for that.
Okay, no problem. Okay, so this is the rule how we build the circuit for a given logic gate, okay? So here on the next slide, on the next slide, we see here that how this was done. So for the pull-down network, we took A and B and C and D and we put them in parallel. For the pull-up, it was the complement. Series became parallel, series became parallel, and their parallel branches became in series, okay? And then the pull-up is between VDD and Y, and the pull-down is between ground and Y. Okay, now they're telling me here that I could have implemented the same function as A and B or nor C and D, right? So if I have in CMOS, if you have noticed, the CMOS gates are typically all inverting, right? So to implement an AND, I really need here an AND followed by an inverter, right? And the same here, to implement the AND, I need an AND followed by an inverter. So if I want to count the number of transistors that I need, an AND, based on what we saw before, has 4 transistors, right? An inverter has 2 transistors, and or a 2 input. These are all 2 input, right? And a NOR 2 input has also 4 transistors. Okay, so based on this, what would it cost me to implement this circuit F? How many transistors do I need? Let me erase and let us make a small noise table here for you to...
16, la.
Yeah, so let us look at here if we make a table. So I need first for A and B, how many transistors? I need NAND plus N. This would be 4 plus 2, 6, right? And then for C and D, I need NAND plus N, it's another 6, right? And then for the NOR, for the final NOR, I need 4, so this becomes equal to 16 transistors, right? Okay. So accordingly, if we look at the implementation here, how many transistors do I have? Eight. Right? So there are trade-offs. Smaller, we cannot keep going up in the number of inputs, but sometimes if we prove that the design implementation is compact and there is no delay penalty, for custom design, we tend to go with these special designed gates, whereas we can go with the traditional basic gates or what we call library gates. And I can tell you that we can build any function from NAND, because I can use the NAND to make inverter, I can use it to make an AND, I can use multiple NANDs to make OR function, and so on and so forth. We will explore these later, but first we are familiarizing ourselves that I can build a basic CMOS gate, a complex gate we call it, because it implements a general function versus using the basic NAND NOR or NOR inverter gates. Okay? Anybody has any questions? Great. Okay. So let us look at this example here. So I have another CMOS compound gate, which is A or B or C into D. So here we will have Y bar. It is equal to A or B or C ANDed with D. So this means I will have the bracket. I will start with the bracket because it is required here. It was given. So I will have A parallel to B parallel to C. So this is A parallel to B parallel to C. Okay. And this whole block is in series with D, right? So this is A parallel to B parallel to C, and this whole block is in series with D. So we will have this whole block in series with D. And then this is my full pull down. It should be between ground and out. So this is my pull down network. Okay. And then we will come and draw the pull up. And so the pull up will be really the complement. So I keep the brackets. I keep the input ordering A, B, C, and D, and then I will start to vary the series to parallel, parallel to series. Yani this becomes series, and this becomes parallel, right? And you can do it by looking at the graph itself. We will have A series to B, series to C. So we will put A series to B, series to C. Sorry about the noise. And then this will all block will be parallel to one transistor, which is D. Okay, so this is D, and the whole block is in parallel. I finished my pull-up network. This network should be between VDD and out. Okay, so this is how we draw our circuit. Okay. Hala, you should be comfortable a little bit with the logic functionality. Yes, Hassan, yeah.
Is there a way to optimize a design in which you use less transistors to have the same result?
This is mapping your function, the behavioral level. Typically, later towards the end of the course, we will learn that NAND representing a function in terms of NAND gates is the most efficient in terms of what they call logical effort, because they tend to have the minimum penalty in terms of delay. And we will discuss this towards the end of the course. But yes, typically a design will start. هلا حنحضر شوي small video. It will start from the logical or behavioral level. We divide it into logical units, and then those logical units, the technology now is tending to go to more regularized small designs. The fabric, the more it is made from small and compact and well-known gates, the better it is. So this is called synthesis, logic synthesis. I have a logical function and I need to synthesize it into gates. So I need to know which gates do I pick. Sometimes we have a pool or a library of gates, and sometimes we do custom design. But yes, the more compact it is, the more efficient it is. In the 90s, maybe they had those tech computers which were the fastest because they were really very well custom designed. Everything was done calculating all possibilities compared to the general library-based design. Okay, thank you, Hassan.
Okay, thank you, Professor.
Okay, هلا we finish those sets of slides. Let us look at the next set and then look at the video. Okay, so if we look at, okay, I think this was it, and I apologize for the noise, but I cannot help much. Okay, so this is a continuation to what we are looking at, and in this continuation we are now talking about possible types of logic. يعني أنا when I have a library for my design, I will tell you مثلا I have inverter, NAND, NOR, and I will have some generic gates, maybe XOR, and I will have some generic gates for special purpose calculation that will simplify, instead of me using NAND followed by OR as we did before, use more compact structures. And these gates, we will call them AND or invert, or we will call them OR and invert. Let's see what's the difference between those two. This is sum of products y equal a dot b dot c or de, and typically I will have branches that are in series a, b, c, right, in parallel to de. This is how my pull down is going to look like, right? So this is for this upper circuit. Okay, the pull up will be complementary. إذا هاي كانت and or حتصير or and. Let us see now if I have this function y equal a or b or c in series with d or e. So the pull down is going to start with the inner block, which is a or b or c, and this whole thing is in series with another block, which is, sorry, d or e. Okay, and this will be between the output and ground. Okay, so let us inspect this upper gate and let us see how many products does it have. So I apologize for the noise. How many products does this upper term have? 2. It's the sum of 2 products, right? So I will call it AOI, and I have 2 entries to fill. The first product has how many inputs? 3. And the second product has how many inputs? 2. So we call this AOI 3, 2. ليش؟ لأن I can have any inputs come to this gate. They don't have to be A, B, C, or D. So that's how the library is characterized. Now let us look at the lower gate. And in this lower gate, which is OR times AND and inverted. يعني I have 2 products, 2 sums, sorry, with a product of these sums. So this is an OR at the innermost, then it's an AND of all of these sums, okay, and then I have the inversion, okay. I have 2 sums here, so I have 2 entries to fill. The first sum consists of 3 inputs, so this is a 3. The second sum consists of 2 inputs, so this is 2. So in my library, I will call such a structure OAI32, and this is really based on the original term, and this is how the pull down network is going to look like. Is this clear?
Yes.
Okay, excellent. Okay, so هدول types of gates. هلا I have other things to look into, and let me duplicate this. So let us sorry. Okay, so let us look at the second set of pardon me. Let us look at the second set of constraints or conditions that we want to study. Okay, the second set, it tells me, well, what if my expression cannot be implemented with a real CMOS gate? نحن اتفقنا إنه CMOS gate we can write it as y equals some AB or CD bar, right? So this expression does not have a big bar on top of it. What this means is that I will end up with needing to invert some of the inputs. We have 2 options. The first option is to rewrite the expression using double inversion. يعني أنا إذا عندي y equal a, I can always write it as a bar bar, right? Expand the inner bar and keep the outer bar. يصير عندي الفورمات مثل ما أنا معودة عليها. The same way I'm used to it. يعني إذا أنا عندي y equal ab bar c or d bar e, okay, I'm going to put two bars here. Okay, this is the first bar and this is the second bar. I'm going to expand the blue. Okay, بشكل إنه الواي تصير هي عبارة عن some blue entry which is barred. Okay, طيب how do I expand the blue? شو بصير عندي? What do I get here? The inverse of A or B شو بصير? It is the end of A bar. يعني عندي A, B bar, C all inverted times D bar E all inverted. Is this correct? I broke the blue bar into the bar of the inverse of two quantities. Is this clear?
Yes.
Yes.
Okay, great. So now we will have here حيخلي الجرين بار وحنلحق البلو bar. What will happen to it? So I will expand all of these quantities. What is A, B bar, C barred?
A bar plus B plus C bar.
Okay, so this is A bar or B or C bar, right? Ended with what is D bar, E bar? It's D or E bar, right? Okay.
Yes.
So what we will end up with now is the following. We will end up with, let us write it on top, y is equal to the bar of, and let us see what I get here, bar of A bar or B or C bar into D or E bar. Okay. هلا, the way I'm going to look at this is in this fashion. It's as if somebody told me that this is X or Y or Z into E or G or F all barred, okay? And I know how to draw the pull-down network for this. I have three blocks here, right? I have X or Y or Z, all of them in parallel, right? And these are in series with G or F, which are in parallel, okay? But is this really G and F and this will be between ground and out? This is my pull-down network. We know how to draw the circuit, right? Okay, how does this correspond to this? How do I need to rename the inputs? هاي حدلها X شيء. شو بحط محل هول inputs هلا؟
PMOS.
لا. Let me duplicate this slide and it's too squeezed. One second. Keep. So let me, okay. So let us look at this. No, let's see.
We just replace them by the ones above them. Yani X bar.
Okay. So we have now all of a sudden, let me come back here and let me delete my text. Okay. And now all of a sudden I have, okay. Okay. So now I have this. Let me see. What do I have from here? I want to implement y equal A bar or B or C bar into D or E bar all barred. If I treat this as كلها سوا كأنه عفوا sorry كأنه هيدي هي X وهيدي هي Y وهيدي هي Z وهيدي هي G وهيدي هي F. Do we know how to draw this?
Yes.
Okay,
But
I will get this structure. I will get X parallel Y parallel Z وكلها in series مع G parallel F, right? And this will be between ground. This is the pull down, and this will be out.
بس
Right? Yes.
let's say you wanted to keep لما نغيره على XYZ مش محل البار بنصير نحط PMOS محل NMOS أو مش هيك؟
لا بالCMOS gate, in the CMOS gate, sorry, بس I forget the pen. For CMOS, we will keep the pull up as PMOS, we will keep the pull down as NMOS. We're not going to change this. يعني لنوصل على ground بده يكون عندي NMOS path. Okay, so what will we do? I know that this is a smart way of thinking about it, but what will I do now? I will literally say that my X is really A bar, right? My Y is B and my Z is C bar. Okay, so I'm going to have here A bar, B, C bar, right? And then D and then E bar. Okay, now you will tell me, but I don't have A bar. What is A bar really?
We just invert it.
It is an inversion of A. So to realize it, I need an extra inverter. The same for this and the same for this. Okay? Is this somehow clear?
Yes.
Yes, bro.
Okay, great. So لكينا what we end up having is that we will try to build it from the inverted inputs. Another possibility how to build it, let us see how to build it. Let me duplicate this and let us take it here. So another way they recommend that we can also build it is to look at directly draw the NMOS network from Y bar. Yani instead of doing the double inversion, if I tell you that Y equal A, B bar C or D bar E, okay, find what Y bar is. Y bar is equal to the bar of this expression, right? Okay, just like what we did now. Okay, and this will end up being A bar or B or C bar into D or E bar. Okay, and now I can draw this and I will treat the inputs as we said as the whole A bar, the whole C bar, the whole B, D or E bar. Okay, so you can think of it either way, you will get the same answer. Okay, so great. Let us now look at this gate, at this CMOS gate implementation. For this CMOS gate implementation, I don't have the typical network that I know how to draw. Somebody drew it because they found that it is optimal. Now this is the output node, okay? And sorry, let me take this is the output node here, okay? And this is the ground. So here I have the pull down network drawn for me. How many passes I can have between the output and ground? Show me a possible path which allow me to connect to ground from the output. And I want to write the equation for Y bar equal فيني انزل AD, right? Or ACE, right? Or sorry, I lost connection, sorry. Can you hear me now?
Yes.
Okay. So we have 4 possible paths that we can connect Y to the output. Let us draw them in different colors. The first 2 straight paths in AD or BE. And then I have 2 other paths which are ACE or I have another path which is B, C, D. Okay, so عندي 4 expressions which I can use in my OR. Now, if I want to implement it this way, using this expression here, the traditional way, I do not look at an input as 1, because every expression, this is what is this? This is AND or invert, right? This is an AOI expression. هيدي is an AOI expression. How many products it has? 4, right? The sum of 4 products. The first one has 2, the second one has 3, the third one has 3, and the last one has 2. So this is really AOI 2, 3, 3, 2. Okay? And in this circuit, how many transistors do I need to implement it? Insul A, B, C, D, E.
5.
How many?
5, no?
طلع على pull down. In this one here, it is 5. In this one here, how many transistors? To implement AOI 2332. يعني أنا إذا جيت I will enter for you
6.
let us take هيك blindly without seeing it from Karen. If I tell you in a question I want you to build AOI 2332 شو بتجوا بتعملوا انتم بالpull down؟ تعملوا لي 4 branches ORed in parallel صح؟ أول branch فيه 2 صح؟ تاني branch it has 3. ثالث branch it has 3. And the fourth branch it has 2. And all of these are between ground and out. Am I correct? And this is for the pull down. Does this correspond to the pull down of an AOI 2332 يلي هي A, B or C, D, E or F, G or H, I?
Yes.
Yes.
Okay. So إذا البول داون أخذت قديش 2 plus 3 plus 3 plus 2 قديه هاي 10 transistors. This means that the pull up will also be 10. The total number is how many?
20.
20. Now, إذا بدي أجي أجيب general purpose gate and implement this function يلي عطاني إياه بالprevious slide، حأجي فوت A على أول branch وتاني branch صح؟ so حتجي ال A لهون وال A لهون، حتجي هاي AB or A or عفوا AD or CE, right? Or ACE. And then I will pass also BE or BCD, right? So حجيب هون BE or BCD. So this is an example where the traditional library gates will be very costly, and thinking to optimize it in an untraditional fashion will help. بس طبعا حيكون ما فينا نعملها mapping by dual. It will be a little bit more complex to get the PMOS gate. مثل بدنا نعمل ال pull down in its own way and the pull up based on its expression and build it more compactly. Okay? بس أهم شيء for me is that you understood the connection between the expanded expression as a function of AOI and the compact implementation that this designer came up with. So عمل لي non-series parallel gates. Okay? Okay. Great.
But Professor, in this case, we need inverters as well, no?
For the pull down?
I mean,
This one here is not inversion. This is a mistake here. It is not. It is. Let us look at the expression on the next slide. So the expression is Y equal to AD or ACE or BCD or BE all barred.
oh,
Is
okay.
any of the inputs inverted? No. لأن احنا what we wrote here was Y bar. لأن
Okay.
عطاني because he gave me the pull down, I drew Y bar in terms of the ending of the inputs. Okay.
Okay, thank you.
Okay, thank you. Anybody has any other questions? طيب هلا the last thing that we have here هيدي هيك مثل last note. We are looking here at a series of PMOS gates. نحن على طول we went to y bar equal to A or B. We said draw the pull up as the dual of the pull down. Okay? I'm just trying to tell you that we could have thought of the pull up independently. يلي إذا جينا قلنا إنه y هي A or B bar وفرطناها حتطلع it is A bar times B bar. ساعتها إذا أنا بس عم برسم directly the pull up from the expression of y مش مثل ما نحن عملنا بس هاي for your information don't follow this approach. فيني اجي اقول ال A bar هي PMOS in series مع another PMOS. Okay, so this is what the and corresponds to. Okay, and this would represent the A bar series مع B bar implemented in PMOS using the Y expression. Okay, بس نحن for us we will not do this. We will only focus on earlier approach. Okay, so we will only use conventional methods اللي نحن عم نستعملها. اوكي حدا عنده سؤال؟ يلي من هاي بنطلع y bar ونطلع ال y as the اوكي
دكتور
yes.
non series parallel فيك ترجع تقولي ما فهمت شو what's special about them.
Okay, what was special about it? Let me بس let me repeat it 1 second. I'll remove all the animation. Okay, هاي خليها. Okay, you understood up till here that I can expand it how I end up. مش هي عفوا sorry. ال non-series parallel هاي. Okay, let me remove it. Okay, so you have this circuit, you have this expression. Let us start with this expression here, okay? If I start from this expression here, y equal AD or ACE or BCD or BE bar, كيف كنا رسمنا نحن؟ كنا جينا قلنا y bar equal AD or ACE or BCD or BE. If I want to draw it in the series parallel, I cannot treat one input, the inputs in non-common أو شيء. I will look at it. What does this look mostly like? It looks like A series with D, right? Okay. Parallel to A series with C, series with E. So I have to treat this as if all the inputs are different. يعني the easiest way for me to think about it is to say AOI مش هيدي هي AOI of what?
Yes صح 2332 yes
2332
yeah.
طيب أنا بعرف كيف to implement the AOI 2332 هيك كم ترانزستور أخذتني البول داون؟
20
10 pull down 10 pull up exactly. Okay.
Yes.
بينما another designer said wait I can see if I can reduce the area by benefiting from the fact that the inputs are common. Okay, that I have some common inputs that share certain paths to ground مثل ال B will be. I could not factor it easily, but I could plug in a non-series parallel transistor to allow me to establish the paths to ground with less number of transistors. يعني هاي logically I cannot write it, I cannot factor it, but mentally the designer was able to build this circuit this way. If we inspect his circuit, we find that we satisfy those different expressions. Okay, يعني A, C, E, B, C, D, or this using this drawn structure, and I can connect Y to E based on this equation using this non-conventional using the transistor to connect between those two parallel branches. Okay.
اوكي بس هون بس عنده كأنه pull down circuit انه وين البول اب؟
ايه لأن البول اب اللي له مفرق جايينكم هنا. اوكي.
اوكي بس في
هلا
بول
if
اب.
you
اوكي
draw it conventionally you draw it from this and go up. أي parallel دي series مع هيدول. The pull up needs also custom design, so we did not show it to you here. So here we have only pull down. Okay. Okay, thank you. طب, okay, هلا I'm going to